We present high-dimensional convolutional networks for geometric pattern recognition. Finding structure in noisy data is a general problem that arises in machine learning and computer vision. Thus, many algorithms have been proposed over the years to cope with noise. Some of the representative approaches include random sample consensus, robust statistics, and consensus maximization. Recent work has begun to leverage deep networks for geometric registration for 3D point cloud registration and 2D image matching. All of these works employ variants of point nets to classify inliers in an unordered set of putative correspondences. In this work, we show that correspondences form a geometric structure in a high-dimensional space and propose convolutional neural networks for finding such geometric structures. We first discuss the geometry of 3D correspondences. Let x, y, z 1 and 2 to be a correspondence. A correct correspondence will satisfy the transformation equation. If we reorganize the equation by concatenating coordinates, we get three hyperplane equations. In other words, inliers form a 3D plane in a 6D space, whereas outliers will form noise outside the plane. Similarly, let uv1 and uv2 to be a correspondence. A correct correspondence will satisfy the epipolar constraint. If we expand the equation, we get a quadratic equation. And the solution of the quadratic equation forms an ellipse, parabola, or a hyperbola, and these are known as conic sections. Thus, the 2D correspondences that satisfy the constraint will lie on the 4D hyperconic section. And others will be noise. In conclusion, 2D and 3D correspondences form a low-dimensional geometric structures in high-dimensional spaces. In other words, finding these geometric patterns is equivalent to finding inliers. And finding the inliers requires segmenting them from the noise. Then, what algorithms are good at segmentation? In the image domain, we know that convolutional neural networks are proven to be effective. Similarly, a 3D convolutional neural network has achieved state-of-the-art performance in point cloud semantic segmentation. Although these networks use different tensor representations, in both cases, convolutional networks are the most successful method for segmentation. Thus, to segment the basic low-dimensional geometries, we propose using an n-dimensional convolutional network. We created a U-shaped convolutional network with residual connections within blocks and across the network similar to the standard segmentation networks. We use the generalized convolution to implement convolution, since it can model both spatially dense kernels and spatially sparse kernels, which are crucial for high-dimensional conv-nets. As a simple diagnostics test, we created a simple dataset of lines in high-dimensional spaces. This is a two-dimensional projection of a subsampled 8-dimensional line in noise. The task of the network is to predict the foreground probabilities for all points given only the coordinates. For the baselines, we use point net variance and measured the F1 score on the test split. Chi et al. Failed to achieve a good performance. Augmented Zaire et al. And Yi et al. Achieve good performance but fail beyond 24-dimensional spaces. However, ours achieve high F1 scores on all dimensions. Similarly, we also created a plane dataset, which we visualized here. On this dataset, all baselines fail beyond 16-dimensional spaces, but ours maintained a reasonable performance. Next, we test the convolutional network on real datasets. First, we use a 6D convolutional network to detect the geometric structure the 3D correspondences form and segment the inliers. We use the 3D match dataset for this experiment and use the FPFH, a hand-designed feature, for feature matching. The network is trained to segment the inliers and we fed correspondences that achieve high foreground probabilities to registration and measure the registration success rate. When we use a registration algorithm, FGR, without an outlier filtering, it achieves around 40% success rate. Registration with Yi et al. For outlier filtering, it achieves below 60%. On the other hand, we were able to achieve more than 70% success rate. Here, we visualize the 100 random correspondences before and after the outlier filtering with a 6D convolutional network. Finally, we use a 2D image registration dataset to validate a 4D convolutional network. In this experiment, we use a popular photo tourism dataset, YFCC 100 million dataset to train and test our method. We use a U-shaped network and use the SIFT correspondences to create 4D inputs. We use the F1 score as our main metric. On the YFCC test set, LMEDs and MLESAC achieve below 0.4. Point net variance including LFGC and OA net achieve around 0.7. We test our networks with few variants and our method with spatial correlation module and ours with UCN achieve above 0.8. We visualize the correspondences and predicted inliers of each method in green. Note that ours achieve more accurate predictions in some cases. Please visit our project page for more information.